Great, thank you. So my name is Gabriel Casabona. I am a physics PhD student at Northwestern University, where I study astrophysics.
When I woke up this morning, it was a bit late, but I didn't care, so I just went ahead and prepared myself. Then I looked at the mirror, my eye was good, so I said to myself, I'm ready.
I did my master's also in physics at the University of Massachusetts Dartmouth, where I got first introduced into astrophysics. And overall, what I study is how certain types of objects in space explode, what sorts of exotic physics we can learn from it. And I'm mostly focused on two things. One is what elements are formed in these explosions, and then what other ways can we detect that these explosions are happening. So the first thing is I study a class of stars called compact objects. And what a compact object is, the remnant of a star that has exploded and died. And so these are called supernovas when the star reaches the end of its life. And these types of supernova I don't study directly, but the main idea is that when a star gets really old in the star's life, it's constantly burning hydrogen at its core. So it's constant like nuclear fusion, nuclear reactions happening. And you can think of it as like a bunch of tiny explosions, or not tiny, but they're like huge explosions that happen throughout its entire lifetime. And that's like the pressure and the force that's keeping the star expanded, but then the gravitational pull of the star itself keeps it together. So it's constantly in this, what we call like a static equilibrium, where the gravity holds it in, but the nuclear pressure is trying to push it out. At the end of a star's life, it runs out of fuel to keep burning. And so eventually the gravitational pull gets too much for it to handle and it collapses. And once it gets down to a certain size where all of that plasma around the sun or around that star gets really close to the core, it's very unstable, it's very hot, very dense, and there's a lot of fusion happening. So a lot of heavy elements are being formed, and that causes what we call the bounce, and the star just explodes. It will literally just eject out in these really huge explosions, and it will leave behind some kind of object usually. So stars that are whatever the lower mass limit for a star is, up to about 9 solar masses, so 9 times the mass of our sun, will leave behind an object called the white dwarf. And a white dwarf, you could think of it's such a dense object. Imagine you take the sun and you compress it down to about the size of the earth or the moon. And the reason why it's so dense, it's made up of what we call degenerate matter. Now, there's some nuances there, but essentially what it means is that in the explosion, when the star first exploded, that explosion doesn't start at the very center. It starts just outside the core. So the energy pushing the material out also pushes the core in. And so it rapidly compresses down to these compact objects. And a white dwarf is compact enough that it now becomes electron degenerate. And what that means sort of is that you compact the electrons that are very high energy, and you compact them to the point that they begin to fill up what we call like these Fermi energy levels. I think you may have had like a nuclear physicist on some point, so they probably explained this. But long story short, these objects are incredibly dense, and because they're degenerate, the more massive they get, the smaller they get, whereas everything else in the universe follows the exact opposite rule. So a star or a white dwarf about the mass of our sun is about the size of the earth. If you go to a white dwarf at its mass limit, we call it the Chandrasekhar mass limit, which is about 1.5 solar masses. That's about the size of the moon. So the next class of objects, for stars that are like 10 solar masses up to about 30, they leave behind an object called a neutron star. A neutron star, imagine you take the sun and you compress it down to about the size of New York City. So it's only about like 25 kilometers big, very, very dense, very exotic. No one really understands what a neutron star is because it's so hard to detect these in space. And they're also very rare. So like I was mentioning before about the white dwarf, 99% of stars fall under that category where they will leave behind a white dwarf. 0.9% of stars will leave behind a neutron star. A neutron star is similar to to a white dwarf in the sense that it has neutron degeneracy rather than electron. What that means physically, I don't understand too well, but it allows it to be even denser and even more exotic than a white dwarf. And then stars that are 30 solar masses and up, which is about 0.1% of stars, daily behind a black hole. Now, a black hole is the strangest object that we know of. No one really knows what's happening inside, but there's plenty of very bright scientists trying to figure this out. But a black hole is like, I think it's something like, imagine taking the sun and you compress it down to the size of like an orange. So it's like a little bit bigger than my fist, sort of. So the first part of my research that I started at UMass was to study what's called a type 1a supernova. So do you see a periodic table in front of you? Let me just explain what this is. So in any chemistry course, you probably learn about the periodic table. This is like the chemist's way of trying to organize the elements. This particular form, we call it the astronomical periodic table. And so it's color coded so that you can see and get a feel for where in the universe these elements are created. So the first two elements, hydrogen and helium, those are mostly formed in the Big Bang. Something like I think it took maybe a couple 100,000 of years after the Big Bang to let the universe cool down because it was so hot and crazy that these quarks that form these elements, it was too hot for them to fuse. So we had to wait for them to cool off, and then we created mostly hydrogen with some helium, and then very small amounts of lithium. The next two elements, beryllium and boron, so number 4 and 5, are made from cosmic ray fission. This is more just like you have random bits of energy and particles just flying throughout the universe, and every now and then they'll collide with the smaller elements like hydrogen and helium, and then you can make these smaller ones. Now, carbon and nitrogen, 6 and 7 here. This is both in dying low mass stars and exploding massive stars. So this is where I was saying before, these stars, there's constant nuclear fusion happening at its core. And for what we call like first generation stars, so like some of the oldest stars in the universe, they will fuse up to heavy elements like carbon and nitrogen. And I think for some, they can also fuse up to iron. But in the green, where it says exploding massive stars, this is where the majority of the heavier elements past nitrogen get synthesized. So lighter stars, when they explode, are more going to fuse stuff like between oxygen to, let's say, magnesium. And then the more and more massive star, you begin to get all the way through rubidium, number 37. So white dwarfs can also explode, even though they're the remnants of a star that already died. And this is the first thing that I addressed in my research at UMass was how can we get a white dwarf to explode? We call these explosions type 1a supernova. Supernovae are categorized. The first categorization is type 1 and 2. So when astronomers are looking out in the universe and they see these bright flashes of light, you can determine what elements that light came from. It's called spectroscopy. And if the light contains hydrogen, which is like the first element that we talked about, we call those type 2. And if there's no hydrogen, they're type 1. And then if there are strong silicon lines, which is element 14 in the periodic table, we call that type 1a. And type 1a supernovae are extremely important. You may have heard this big rumor going around that the universe is expanding, and it's expanding at an accelerated rate. We call this dark energy. The reason we know this is through observations of type 1a's, because type 1a's have a peak luminosity that's very consistent. And so because the luminosity is very consistent, we call these standardizable candles. So basically, by looking at the brightness of these explosions, and then also something called redshifting. Redshifting is a phenomenon, when you, like if you're out like in the street somewhere, and there's let's say a police or ambulance driving by you with a siren on, and the pitch of the sound changes as the car comes towards you. Like it gets higher and then it gets lower as it goes away. That same thing happens with light. So when these explosions are happening in some galaxy very far away, all but one galaxy, as far as we know, are all accelerating away from us. And so what you can imagine is when this explosion happens and the light beams towards us, the source of that explosion is also moving away from us, and it'll stretch the photons out. It'll stretch that light out, very similar to how the sound of these cars gets stretched and compressed, right? So it's like when the ambulance goes away from you, the pitch lowers. So when the light, when the source of these lights are moving away from us, the light gets stretched out and it becomes redder. So photons are characterized either by its energy or its wavelength. Higher wavelength is more of the red side, and shorter wavelength is the blue side. So redshift means that it's been stretched out so that it's now redder. If it were the case that the object was moving towards us, which is rare, but it does happen, it would be blue shifted. So it would look bluer than what it really is. So all these things together, we were able to determine that not only is the universe expanding, but it's expanding at an accelerated rate, because the farther we look out, galaxies that are farther and farther away are moving faster and faster away from us. And that's all thanks to the discoveries of these Type 1As. And so although we know about these Type 1As and it's been confirmed that Type 1As are the explosions of white dwarfs, it's been a puzzle that astrophysicists have been trying to solve now for several decades on how can we get such a strange object to explode. So for some further organization, we do now think that the major piece of the puzzle about how these white dwarfs explode, that they are in a binary system. So from what we understand about stars and stellar evolution and how they're formed, the majority of stars in the universe exist in pairs. So it's rare to find a star by itself. Like our sun is by itself, as far as we know. But most stars exist in these binary pairs, and they basically just do this dance around one another for their entire lives. And in these cases, one of these stars eventually will explode. And so again, these explosions can leave behind a white dwarf, neutron star, or black hole. And in the case where it's a white dwarf, because the white dwarf is so massive but so dense, it can get really close to its companion star and begin accreting mass off of it. So here we have this is more of an artist rendition, not really a simulation, and this was done by NASA. So what we're seeing here is the white dwarf, and in this particular movie, this is another white dwarf, the bigger one. Because the white dwarf, so again, the smaller white dwarf is more massive, right? So it's going to be pulling on the matter on the other white dwarf, and that matter will begin to fall into this white dwarf until some point that it explodes, which we see here. And then one of the byproducts is that surviving star gets flung out into the universe at really, really high speeds, which we have detected. We've detected a handful of these in the past year or so within our own galaxy, closer to the galactic center. So just for some terminology, if that white dwarf is with another white dwarf like we saw here, we call this the double degenerate channel, meaning that there's just two degenerate objects. If the other star is just another main sequence star, we call that a single degenerate. We believe, we as in me and my old advisor and my collaborators, that it's much more likely that the case that I just showed you is what's happening, is that you have two white dwarfs in this system, and that primary white dwarf will accrete mass from another white dwarf, explode, and then send these poor little white dwarfs just flying through the galaxy. So what we do to study these, so that, as I said before, I do astrophysics research. Unlike most sciences, we can't just do experiments, right? We can't sit there and recreate the conditions of a star or a white dwarf. So what we do instead is we perform simulations on computers. And what that means essentially, so all of physics and most of science in general can be described in equations. We call these differential equations. Equations are such that we as humans can't solve them on paper. The majority of realistic systems in the universe can't be solved what we call analytically. Instead, we solve it numerically. And to do that, we set up, we first model whatever we're looking at into these systems of equations, and then we type out some code in whatever our favorite language is, like C, Fortran, and we write it in such a way that it begins to solve these equations. For large, computationally heavy problems like this one, we can't just solve it on, let's say, my laptop. Instead, we have to use a supercomputer. So for this this simulation that I'm going to show you, we used a supercomputer out in Texas called Stampede 2. where we use hundreds of thousands of computers at the same time, all to solve this same problem. And we take that, we grab those solutions, and then we come back and make nice plots in movies like this one. So what we did here was the white dwarf that's exploded is a couple of thousand kilometers big. So we wanted to see, can we get a piece of that white dwarf to explode? So we zoomed in to about 100-kilometer wide box. So it's about a tenth of the size of the whole thing. And we started off these simulations by injecting degenerate matter, like I described before. And these white dwarfs have mostly a carbon-oxygen core with like a little bit of helium on the outside. And so the goal is to detonate the carbon. And what that means is that instead of just having it fuse together, so like carbon coming together, when they fuse, we call that nuclear burning. In the location where that burning occurs, we call it a flame. And if that burning propagates faster than the speed of sound in that material, we have a detonation. If not, it's called a deflagration, and it just continues burning. So here we modeled what that would look like, and we actually do have a successful detonation, which we see up in this corner, this white spot here. So this white spot, again, we're looking at a 100-kilometer cube box. We're looking through the z-axis, and the color coding here is the energy that's being emitted by those nuclear reactions. And it's on a log scale, so it's about 6 orders of magnitude difference here. So this white spot is where that detonation is occurring, with that border here being the line. That's like the shock wave that's propagating through the whole star. So this is a short simulation because it's kind of expensive. But so long story short, we were successful in figuring this out. In this scenario here, when the matter is falling onto the white dwarf, it's crashing down and mixing with the material that's already on this white dwarf. And so this leads to a very turbulent environment. Turbulent meaning like you hold a cup of coffee and you pour milk in it. Well, that milk is, let's say, crashing down onto the coffee and then begins to mix in, right? And turbulence is involved in making sure that all the milk gets mixed in, and that's kind of what's happening here. Is you have this turbulent mixing occurring, and what we found was that turbulence itself is responsible for allowing a detonation to occur in the first place. So that was the main idea for that first project, and we were able to determine that this was a very viable mechanism for how white dwarfs can explode. So then I continued it, and one thing that I mentioned briefly was that although these white dwarfs are mostly carbon and oxygen, there's a very thin layer of helium on the outside. So this particular movie uses a mechanism. It's called the D6 mechanism. Now that's dynamically driven, double degenerate, double detonation. So dynamically driven, the first two Ds, it just means this first part of the movie where you just have this constant influx of matter. Double degenerate because it's two white dwarfs, like I mentioned before. And then double detonation, this is an idea that's been circulated around the community, where in order to get that carbon to detonate in the first place, you have to detonate the helium outside of it first. And so for my next project, and something that I'm working currently on a paper on, the idea here is that if you have your main white dwarf and then the small helium layer outside of it, if you can get any two individual pieces of the helium to detonate, it'll send a shock wave into the core, into the carbon core, and that can cause a detonation in the carbon. So that's where the double detonation comes from. So what I did was I took the same physics that I just described before with allowing the mixing, or like allowing the turbulence to detonate carbon. I did the same thing, but now I started playing around with what happens if you put in helium. And there's a variety of results. I'm still wrapping up the results into a paper. But one of the results is that if you get the combination just right, then you'll end up with helium detonating, but then not the carbon. And that's what this movie here shows, is that's helium blows up, but it doesn't detonate the rest of the carbon. And so it kind of just like sloshes around the rest of the material, which is what we see here. And the reason why it changes color is because the energy is changing pretty drastically. So I'll show that again. And this is the same idea. We run these huge simulations using some thousands of of computers, and yeah, this is currently being written up into a paper. So, all right, so what I'm doing now. So first, I talked about looking at what happens when two white dwarfs come together. We call that a type 1a supernova. Now, the field as a whole of studying what happens when these exotic objects come together, it's compact binary object mergers. So I just talked about two white dwarfs coming together. Now let's talk about what happens when two neutron stars come together. And this is where things get much weirder. I don't think that a proper simulation of this exists yet, but the idea is, let's say you have these two neutron stars. They're dancing around each other for some billions of years, and they finally get really close to one another. Now, again, these are very, very dense objects, so they can get very close before touching. Now, whichever is the more massive one will begin to shred the least massive one, similar to the other video that I just showed you. And when they coalesce, when they're about to touch one another, they release an exorbitant amount of energy while also forming a black hole at its center, leaving the rest of the material as a disk around it, right? So a part of that, we think, is that because these degenerate objects they will become more massive, or they become smaller the more massive they get. If you're continuously packing on more of that material onto that neutron star, it's actually getting smaller and smaller. And so once they touch, they now become small enough to collapse under its own gravity, forming a black hole. And then whatever unlucky material gets left behind gets stuck in this disk. So now we end up with this black hole with a disk of this exotic matter, and it's spinning around really fast. Now, one of the things that happens, the black hole, right? So it sucks in everything. Now, the matter that was once these neutron stars is highly magnetized, and so the magnetic field lines are going through the black hole. And in these scenarios, black holes are spinning. And there's a very strange thing that happens where when the black hole begins to spin, it takes these magnetic field lines and wraps it around it, forming a huge column of magnetic field. And the material that was in the disk can get trapped in that and form what we call jets, an astrophysical jet. And that's exactly what we see in this movie here. So the green and blue is the disk. There's a black hole in the center of this. This blue and green material was once the neutron star. And this simulation begins after the jets have already formed, which is what's in orange and red. In this particular scenario, one of the things that my advisor found a few years ago with some of his other students is that if you have a disk that's rotating or that's orbiting around this black hole, and the black hole has spin, if that spin of the black hole is not perfectly aligned with the rotation of the disk, you can break the disk. And that's actually what happens here. If you see this blue part here where my mouse is, this is a broken disk. And this other piece here is the rest of it. And so when this happens, you let this run long enough, you end up with the jet being broken apart, like here. And the disk itself keeps breaking inside. And the reason why this is important is because we see this happening in space. We don't see the disks themselves breaking, but we can detect jets like this. Jets like this are occurring in just about every galaxy. At the center of every galaxy, or almost every one, there's a supermassive black hole. So a black hole like anywhere from like millions to billions solar masses. And and they periodically are absorbing matter around it. So regardless of if it's like what used to be a neutron star or any other star, something like this will occur where the disk, what used to be that star now becomes a disk, and then this whole thing, this whole scenario happens. Now, if that jet is facing us, this is all like in the study of what we call active galactic nuclei. If that jet is facing us, I believe we call it a quasar or a blazar. I forgot which one it is, but we can see these jets, and they're very, very bright flashes of light. Every now and then, we see these bright jets, and they flicker in a weird way. And so what we think that's happening is that this mechanism is taking place. So the disk itself is breaking apart that jet, and this is an attempt of trying to explain what we already see happening in space. A part of this reaction, so when these neutron stars come together, there's an initial explosion that occurs. And this explosion is called a kilonova. So for terminology, kilonova and supernova, a nova is some other type of explosion that happens in space. And so a supernova is 1 billion times brighter than that nova. Kilonova is only 1,000 times, but it's still very energetic. In the kilonova, which we have detected, the event was called the GW 170817, meaning we detected it August 17th of 2017. So we actually detected something like this for the very first time just like 3 years ago. Actually, I think, what's today, the 20th, so almost like 3 years to the day. And what happens is these neutron stars come together, and at the same time that a black hole forms, an explosion also occurs. And that explosion is the kilonova that we see, and then the rest of the material kind of just sits there and it forms a disk from the jets like we're seeing here. So we detected this explosion, and we detected it 3 different ways. The first was the light. All these explosions emit great amount of light. They also emit something called neutrinos. Now, neutrinos are really weird objects. I think they're like the second lightest particle that we know of, where photons would be the lightest because they technically have no mass. We detected these neutrinos as well. So we detected the light from just telescopes from like various observation places around the Earth. The neutrinos we detected in a really cool experiment where one of the places down in Antarctica, which there are scientists who live and work down there, and they set up this huge experiment where they have these giant metal rods going into the ice of Antarctica deep enough so that it can not interfere with any of the other radiation passing through Earth. So at any given point, there's a flux of particles and energy passing right through us. So they're trying to avoid any of those by going deep underground. And what happens is these neutrinos, although they're very, very small, so they hardly ever interact, if there's some event that's really energetic, emitting a bunch of them, there's a higher chance that it'll react with one of these metal rods. And I forgot which elements are formed, but the way they keep track of it is that the entire metal rod has one element, I think, and then the neutrinos will come and form the next heavier one, or they will change the chemical composition. Just so happens that we observed this light and that we observed this happening within these experiments. So we know that light and neutrinos were both flying through the galaxy from this one localized event. And then the third way, which is probably the more exciting way, is that we detected it using gravitational waves. Now, gravitational waves are very strange, but the basic idea is that when you have these large, powerful events happening in space, they physically shake space-time. And so we first detected this from the merger of 2 black holes, but really any object or any event like this, so any supernova, type 1a, type 2, these merging neutron stars, merging black holes, they will all emit gravitational waves. At the moment, we can't detect all of that because they're very, very small. But the basic idea of how we detect these, we use laser interferometers, 2 of which we have in America. One is in Louisiana, and the other one is in Washington State. And then for this event, we use a third one out in Italy called Virgo. And the basic idea is you have these 2 lasers that are in an L shape. All right, so you have these 2. And so when this gravitational wave comes, let's say like this, you have a little dance that happens between these lasers. So these lasers will shoot up, reflect back, and when nothing is happening, the light comes in, and it's a phenomenon called, I think it's like constructive coherence. So the spot that the lasers come back to will be brighter than the laser coming out. But if you shift it just a little bit, you see that light begin to dim. And so when these gravitational waves come by, they stretch these lasers. And so that's how we detected it, was because all 3 of those lasers, of these laser interferometers, they all detected the same event. And because they're on different parts of the Earth, you could like localize from what direction it came in. So the information that we got from these gravitational waves, from the light that we observed through telescopes and through those neutrinos, we were able to localize where this event came from. And it was from some galaxy, some like hundreds of millions light years away. So going back to here, these merging neutron stars is actually one of the color codes here. So it's the orange. So you see all of the heaviest elements, you basically require 2 neutron stars to merge. So from this event, 170817, we found elements around this section, so around gold. Oh no, it's here. Gold is AU, so gold and platinum. Now we have never detected any of these elements anywhere in the universe. We've seen countless supernova, we've seen all sorts of events, but we have never seen any of these heavier elements. We call these lanthanides and actinides ever form. And there's really only one of two events that we know of where heavy elements like this can occur. And merging neutron stars so far has been the only one that we've detected. The other one is called the collapsar. So we were able to detect that these heavy elements formed. And so what I'm doing now is I'm trying to just understand the process that led to these heavy elements forming. So there's a lot happening here, but the first thing is going vertically is you're adding the number of protons. So like you're moving along one piece on the periodic table. And then going to the right is the number of neutrons. So you've probably had some other nuclear physicists come on, but all these atoms at the nucleus, we categorize what element it is by the proton, and then we categorize an isotope by the amount of neutrons. So one of the cool things about neutrons is, suppose you have a neutron sitting by itself in space. In about 10 minutes, that neutron will decay. And so a neutron will decay down into a proton, an electron, and an electron antineutrino. So these neutron stars are, again, they're very exotic objects, and they're mostly made up of neutrons, like the name implies. So in this collision, you have an environment that's neutron dense. It's highly energetic, so all the particles are moving around really, really fast, and it's hot, and it's very hot. And these are the right conditions so that you can have these free neutrons that are flying around, and they will fuse onto whatever element is around them. And so if you just focus on this purple line here, that goes around. So what's happening here is if you go to the right, you're adding on a neutron. If you're going up, you're adding on a proton. And so what happens is, so let's say we start from here, whatever this element is. So we slap on a neutron. And so now you move from here and you move over one to the right. Now, once that neutron slaps onto whatever atom that is, if enough time passes, that neutron will decay down into a proton with the other two stuff, and it'll form the heavier element. So whatever element is one above on the periodic table. And that is called the S process. That's called slow neutron capture process. So the neutron has enough time to decay down into a proton before the next neutron comes in. If you are in an environment where multiple neutrons can slap onto this atom before any of them decay down, that's called rapid neutron capture process, or R process for short. And in these environments, so S process usually occurs more in like the explosion of stars, for example. But R process, it's what's needed to form these heavier elements down here, and it's exactly what we see happening in these merging neutron stars. And so you slap on as many neutrons as you can, and there is a limit of how many neutrons you can tack on. Let me see if this other one explains it a little better. So here you can see like as a grid, so it's a little easier to like determine what's a new element. So there's like a boundary on the underlying of this chart. So this is called the this chart has a couple different names. It's called like the nuclear island of stability or something like that. And so you slap on a neutron and you go to the right, and then if that decays, it goes up one. But if you're let's say you're in this small, but you can slap on as many as that element can take, and that's called the neutron drip line, which is the underlying boundary here. And so that's exactly what we need to form these heavy elements. And so what I'm doing now is I'm trying to take the code that performed that last simulation that I showed you, and I'm trying to incorporate the physics of the R process along with my research partners who are also incorporating different types of physics, like the neutrinos, for example, like how these neutrinos are formed. That way we can have one simulation that's robust enough to calculate all these things. At the moment, our group, for these types of simulations, for like accretion and like formation of jets, we have the best code. We have the most accurate with the highest resolution, and we're also using the most powerful supercomputer in the world called Summit, which is out in Oak Ridge National Laboratory in Tennessee. And so that right now only solves like the movement of the material along with how the black hole affects it. But once we're done, once we've completed our our main goal, which will probably take a few years, we will then be able to understand all of the nuclear physics that we need to understand what elements are formed and exactly how are we going to detect this in the future. Anyone can do physics. It's only really if you want to do it or not. There's nothing particularly special about being able to do this. I am not naturally gifted in anything, not math or computer science, but I like physics so much that I was willing to learn it in order to do this as a career. So if you know you want to do this as a career, so getting a PhD mostly is so that you can have a career in research. So if you are passionate enough about physics and you know that you want to do research as a career for the rest of your life, just understand this PhD process takes a long time. Usually it's like 6 years to get a PhD in physics. So just have that in the back of your mind that it's going to take a long time, and just be sure that you're passionate about it, and that when you are applying to a PhD program, the name of the school doesn't matter as much, like the prestigious programs around the world that we all know of. It's what they're doing and who is doing it. You want to be able to enjoy your time there, so you want to be able to work on something you find fun and work with people that you can be very productive and actually have a good time working with. Yeah, so we gotta be careful when we go out to space because we might get hit by a star. So,
No. 1 o'clock.
stay for me.
Yeah.
Oh.
And take
Have a good
care.
night.
Yeah, thank you.
Whoa.
So with that,
Oh, we gotta start now.
yeah, however you want. So yeah. So yeah.
Oh, thank you very much for your time.